Let's see if Jupyter will work. I've been changing some things in my computer settings, so I hope that I can simply type Jupyter Notebook and it will work again. Let's see if that works. Good, here we are. Today we're on lecture 7. We've covered all of the basics of Python and NumPy, and we've started talking about how sound is recorded on a computer. Last time we talked about how sinusoids and sine waves and cosine waves are heard as pure tones, and we talked about how those can be sampled on the computer as long as the sampling rate is at least 2 samples per period. Once every complete period of the cosine, we need to have at least 2 samples. And now that we know that sound is composed of cosines and sines, now we can take advantage of that to analyze natural pure tones. I told you last time that the piano, the note on the piano, the A440 at the center of the piano, includes that cosine wave, but it also includes a number of other frequencies that are multiples of that fundamental frequency. And I want to talk about that today by talking about the idea of a musical chord. So let's just go to Wikipedia and look up musical chords because that will be a good place to start. So a major chord is a set of 3 notes that are arranged in a triad with the base frequency like 200 hertz, and then the center like 250, and the top like 300, and they have to be arranged exactly in whole number ratios of 4 to 5 to 6 in their frequency. So the sound is like this. It's a major third and then a major fifth. So a perfect fifth note and then a major third. So we have the bass note at 200 hertz, and then we go up 2 whole notes or 4 half notes on the piano to 250 hertz, and then we go up another 1.5 whole notes or another 3 half notes to 300 hertz. So we get something like what I just played for you. I also want to talk about the minor chord today. The minor chord um, does the 3 half notes in the first step, and then the 4 half notes in the second step. And so it sounds like this. That's a standard minor chord. Do we have other examples? No, I guess just that one. There are slight variations. So there's the basic minor chord, and here's the basic minor chord again, tuned just slightly differently. The so that's sort of the paradigm that I'm going to use today. I want to talk about how to analyze what the frequencies are in a chord. When you hear that chord, we know that it should be the root note, a minor third, and a perfect fifth, or the root note, a major third, and a perfect fifth. But if you just heard that chord, how would your computer analyze whether it's a major chord or a minor chord? How would your computer be able to analyze exactly what frequencies are there? And the answer is that we take advantage of the fact that each one of those tones individually can be represented as a perfect cosine or sine wave, right? It's not a perfect cosine or sine wave, but the bass note, the fundamental, is a perfect cosine. The pure tone is a perfect cosine or sine wave. And knowing that, we can take advantage of something called the orthogonality principle. Orthogonality means perpendicular. Let's look that up on Wikipedia as well. So orthogonal means perpendicular. It just means perpendicular lines like this. The line AB and the line BC are perpendicular to each other or orthogonal. And one of the things that happens with orthogonality is that if you take a light source directly above A and shine it down on the line A to B, the line A to B has zero shadow on the CD line. Right? So if you can imagine the sun is right above line A and the sun is shining down, these two shadows become zero length. And so that idea that perpendicular lines cast a zero size shadow on one another can be generalized to a zero dot product, and it can be generalized even to things like multiplying together two cosines. So orthogonality generally, two functions are said to be orthogonal if we take the dot product of those two functions and the dot product is zero. And the standard example that I want you to know about is that if we take the cosine at one frequency, say k periods per n samples, and we multiply that by a cosine at a different frequency, say m periods per capital N samples, if we take the dot product of those two by multiplying them sample by sample and adding from n equals 0 to capital N minus 1, that dot product is 0. Right? So for example, let me import NumPy and Matplotlib, and let me create one cosine that has 3 complete periods, one cosine that has 4 complete periods, and I'll take 20 samples of each of those cosines. So I'll take a cosine that has 3 periods in 20 samples, another cosine that has 4 periods in 20 samples. So x will be the cosine that has 3 periods, y will be the cosine that has 4 periods, and then I'm going to multiply those two together. Remember that this asterisk means array multiplication. It means I multiply every single sample, and then I add them together. And when I multiply every single sample and add them together, the sum is going to be 0. Let me just run that and show the result. So here's the 3-period cosine. Here's the 4-period cosine. Here's their product. Notice that their product has a lot of samples that are all over the place. Some are positive, some are negative. But when we add them together, the sum is 10 to the minus 15th power. So the sum is basically 0. This formula, saying that the total is the sum of x times y, that's actually the same as saying that it's the dot product of x and y. Right? The dot product is just the sum of x times y. So if I run this taking the sum of x times y, I get the same result, that it's minus 1.8 times 10 to the minus 15th power. And what that means is that when I multiply them together, I get some positive samples and some negative samples. And when I add all of those up, they balance out exactly. And so that the average value of that product is 0 exactly. Right? So that's kind of nice. That's just like perpendicularity, right? It's like AB casts a size 0 shadow on the line C to D, right? That the shadow is 0, they're perpendicular, they're exactly orthogonal. That's important for us because of the one exception. The only exception is if K is equal to M. If I have two cosines that are exactly the same frequency and I multiply them together, if I do something like this, cosine of 3 periods times the cosine of 3 periods, if these two cosines are exactly the same, then rather than multiplying x times y, I'm actually multiplying x times x, and I'm getting x squared of n. As shown here, x squared of n is always a positive number, right? And if it's always a positive number, then it can't average out to 0. So here, let me create a cosine with 3 periods and another cosine with 3 periods. Let me compute 20 samples of each. So x will be a cosine of 3 periods, and y will be exactly the same thing. And when I multiply those two things together, I don't get 0. I get something where x times y is always positive. You can see that x times y varies between plus 1 and 0. And so its average value is exactly 1/2. Right? The total of x times y is actually, we have 20 samples, and so the total is 1/2 of 20. It's just 10. So when I take x times x and average it over all time, I get 1/2 of its amplitude squared. If it started out with an amplitude of 1, 1 times 1 is 1, and I just take 1/2 of that. And so the average is one half of those 20 samples. That's useful if you want to try to identify which musical chord is being played. So here's the whole formula. The whole formula is that the cosine with k periods multiplied by the cosine with m periods is equal to 0 if k is not m, and it's equal to capital N over 2. So if capital N is 20, it's equal to 10 if k is equal to m, or if k is equal to capital N minus m. That's a special case because, so this last case, k is equal to capital N minus m, that's aliasing. That's just like the aliasing that we heard last time. Let me, instead of setting um, m equals 3, let me set m equals 17, right? I've got a total of 20 samples. And so if I take 17 periods in 20 samples, it will look exactly the same as if it was 3 periods, right? Here's 3 periods, here's 17 periods, but 17 periods looks just like 3 periods because of aliasing. And so again, even though I have a cosine with 3 periods and a cosine with 17 periods, because I have only 20 samples, those are actually the same signal. 17 periods has been aliased back to 20 periods, and the result is still that the average value is 10. And so we get this final formula that if you take the dot product of two different cosines, one with k periods, one with m periods, that dot product is 0 unless k is equal to m or k is equal to m with aliasing. So k is equal to capital N minus m. Those are the two cases in which we get a non-zero dot product between those cosines. All right, why is that useful? The reason that's useful is because if one of these cosines is an audio recording, it's just a recording that we made with our microphone, and we're trying to analyze this audio recording, we can create this second cosine in Python. We can just go in and generate a cosine and multiply it by the first signal and take the average. And by taking the average, if this first signal has no sound at the frequency of the second signal, then their dot product is 0. And so we can identify exactly which frequencies are contained in the first signal by taking x of n, whatever it is, and multiplying it by a cosine whose frequency we control, and checking to see whether the dot product is 0 or not. So that's useful for speech, but it's also useful for things like musical chords. A musical chord is the sum of three different notes. We have the basic frequency at omega naught, which might be 440 hertz if it's an A note, or 250 hertz if it's a C note. We have g to the fourth times omega naught, where g is 2 to the 1/12th, and so this is 4 half steps up the piano, right? We go from C to C sharp, D, D sharp, and then E. So this is the E note, G to the fourth times omega naught N. And then we go up 3 more half steps from E to F, then F sharp, then G. So this capital G, 2 to the 1/12th, we take our bass frequency, which is the A note, and we go up 7 half steps on the piano, and we play the result, and it sounds like this balanced major chord. The minor chord, which has this kind of sad sound, we say that major chords tend to sound happy and minor chords tend to sound sad, is created just by changing the frequency of the center note. The bass note might still be 440 hertz. The top note might be 7 half steps above that. So in an A major chord, this would be A and C sharp and E. This would be A and C and E. Let me see. A sharp, G, A sharp, B, C, C sharp, right? So in a major chord, this would be C sharp, and this would be E. In a minor chord, this would be C, and this would be E. Those are the notes on the piano. So this is an A note, and a C note, and an E note. And this would be an A note, and a C sharp, and an E note, right? When we combine those chords, the result will sound kind of sad if it's a minor chord. It will sound kind of happy if it's a major chord. So let me first create the major chord. G is 2 to the 1/12th power, and I'll take cosine of omega naught n plus the cosine of G to the 4th times omega naught plus the cosine of G to the 7th omega naught, and that will be the major chord. Let me create a major chord and play it back. Right, so that's the major chord. It's the A and the C sharp and the E. If I want to create a minor chord, I take the A, and then I take G cubed times omega naught to get the second frequency, and then I take G to the 7th times omega naught to get the third frequency. And the result sounds like this. So it's commonly said that the major chord sounds happy and the minor chord sounds sad. I'm not sure if that's how you hear it, but let me play it again so you can understand what the difference is that people refer to. That's the happy major chord, and that's the sad minor chord. And now the question is, if you're playing one of these chords, how can the computer tell which one is which? A human can listen to that and say, "Oh, that's a happy major chord. That's a good note." But how can the computer tell which one it is? And the answer is we're going to take advantage of the orthogonality principle. We're going to multiply it by a set of cosines in order to tell what it sounds like. If I just plot it, right? If I just plot n samples of it, so here's 1/20th of a second, right? Here's 1/20th of a second to that minor chord. It's really hard to tell exactly which frequencies are involved here. It doesn't look like a sine wave at all. We know it's a sine wave, right? A minor chord just has three cosines at three different frequencies, but it doesn't look like a cosine if you plot the tone. And so the secret is we're going to take advantage of this formula. Instead of the first note here, we're going to plug in an x of n. So let me just repeat this. It becomes this, and this is if it will be non-zero if x of n contains the frequency two pi k over capital N. Um, There, I think that formula will print right. Let's see. There we go. So if we have an unknown chord, x of n, could you please mute? If we have an unknown chord x of n, and we're trying to understand what is the sound that we're listening to. What notes does it have? Is it a minor chord or is it a major chord? Well, we can multiply it by a cosine at some frequency 2 pi k over capital N, and we know that because of orthogonality, the result will equal 0 if x of n doesn't have any sound at that frequency. It will be non-zero only if x of n has some sound at that particular frequency. And so this is how we're going to analyze, is it a major chord or is it a minor chord? And we're going to do that kind of recognition. So we'll do exactly this frequency. We'll take the cosine of 2 pi k. Let me copy that formula down and put it down below. So we have this formula. We have x of n, and we want to know what frequencies does it contain. Well, we can multiply by the cosine of 2 pi times k times n over capital N, and that'll equal to a positive number if x of n contains that frequency and 0 otherwise. So we want to basically take lots and lots of different frequencies and multiply. We can create a matrix, capital W, whose k-nth element is W of k comma n, is the cosine of 2 pi times little k times little n over capital N. And we can add from n equals 0 to capital N minus 1, x of n multiplied by wk of n. So let me actually put that in a separate formula here, whose k-nth element is wkn equals cosine of 2 pi kn over capital N. There we go. So w of k comma n is the cosine of 2 pi kn over capital N. And so when we add over capital N samples, w of kn times x of n, that'll equal 0 if x of n doesn't have any information at the frequency k, right? And it will equal a positive number if x of n does have information at the frequency k. In matrix notation, we're creating a matrix capital W, and we're multiplying it by the signal, which is we denote with the small x, and we create the Fourier transform, the discrete cosine transform, actually. We create the transform, the spectrum, which we denote by the symbol capital X. So we have capital X of 0 because this first row is 0 frequency, capital X of 1 because the second row is 1 frequency, capital X of k is the kth frequency, and capital X of n, capital N minus 1, that's the n minus first frequency. So let's do that. We'll take 20 samples and we'll create a cosine at frequency 4 cycles. And then I'm going to create a W matrix, which is n by n samples, where W of k comma n will be the cosine of 2 pi times k times little n over capital N. And then I'll just multiply those two matrices. So when I multiply the two, we see that the discrete cosine transform has energy at 0, 1, 2, 3, at 4, right? Because we had a frequency, we had 4 cycles per period. Yeah, we had the frequency 4, it has information, and also at 16 because of aliasing, right? This one over here at 16, 16 is 20 minus 4, right? So k equals 20 minus 4, which is 16. And so this discrete cosine transform shows that the input signal, let me actually plot this as two separate signals. All right, so up here, let me do a stem plot with that. So in the time domain, we have a cosine with 4 complete periods. And in the frequency domain, we have a discrete cosine transform that has, let me say that this has tight layout so that we can read it a little bit better. And let me create axis labels. So the axis label for subfig 0 is time, and the axis label for subfig 1 is frequency. Measured in the number of periods per 20 samples. And let me give it a little bit larger space. All right. So here we have x of n in time. It has 4 complete periods in 20 samples. And here we have capital X in frequency. And you can see that the discrete cosine transform is picked out exactly, that the input has information, has sound at 4 cycles per 20 samples, and it has information at 16 cycles per 20 samples, because 4 and 16 look the same, right? When it's sampled, this aliasing over here at 16 is exactly the same thing as 4. That's how we're going to analyze the major and the minor chord. We want to take that major and minor chord and we want to multiply them by a W matrix like this. We want to multiply them by a W matrix that has every possible frequency on the piano. Basically, we want that W matrix to have one row for every note on the piano, right? And by having one row for every note on the piano, we can pick out exactly which keys on the piano were being pressed. And so I'm going to start out with, rather than trying to sample every note on the piano, I'll just pick 400 samples. And I'll create a 400 by 400 matrix where WKN is the cosine of 2 pi k times n over capital N. And then I'll multiply that with the minor chord with the first 400 samples only of the minor chord. And the result is you can see there are three notes, right? Here's the A, the C, and the E note. And here are the aliased copies of those same three notes. So now we can see, just like here, we had exactly one pure tone. With the minor chord, we have exactly three pure tones. And so we can read off, this is a minor chord. This is a chord. It has three tones. If we use the major chord, we'll get the same kind of view, but with a slightly different middle frequency, right? This middle frequency is shifted over a little bit to the right. And so the difference between the minor chord and the major chord is where is this middle frequency? Right? When we shift back and forth between the major chord and the minor chord, the only thing that shifts is this middle frequency. And so now we ask, how can we tell which chord it is? We need to be able to identify that this peak is happening at 440 hertz. And this peak is happening at the C note, which is about 512 hertz. And this peak is happening at the E note, which is a little bit higher than that, 600 hertz or so. We need to be able to measure those frequencies. So first of all, let's just zoom in. Here's me just zooming in on that minor chord. Here's the first pure tone. Remember, there were 400 samples in the frequency domain. I had 400 samples. And in those 400 samples, the first tone has 20, 21, 22 cycles. 22 cycles in 400 samples. The second tone has 23, 24, 25, 26 cycles in 400 samples, not 25, 26 actually, right? And the third tone has 30, 31, 32, 33 cycles in 400 samples. All right, 22 cycles in 400 samples. That's K over capital N, right? K over capital N is 22 cycles in 400 samples. If we multiply by 2 pi, we get the number of radians per sample. And so we can set that equal to omega. Omega is 2 pi little f over capital F sub s in order to find out, right? The radial frequency is 2 pi f over fs. And here we have 2 pi times k cycles in capital N samples. And that gives us, again, the number of radians per sample. When we set those two versions of omega equal to each other, we find out that the frequency f is the sampling rate, which is 8,000 samples per second, multiplied by k over n. So 22 over 400 times 8,000, 26 over 400 times 8,000, 33 over 400 times 8,000. So we'll set K are the indices between 0 and 400, and F will be the frequency in hertz. And then we'll just replot that same Fourier transform, and we see that the frequencies in hertz are 440 and 520 and 660. So here's the A note at 440, here's the C note at 520, and here's the E note at 660. And so now we know exactly which frequencies those are. 520 is a minor third. And since it's a minor, right, this is a lower note at 520, so we know this must be a minor third. If we plotted the major third, let's see, capital X I got by multiplying W times the minor chord, right? So instead, let me multiply W times the major chord. If I multiply W times the major chord, then I'll get a slightly different third middle note. Right now, the middle note moves up to 560 hertz, and so now we have four half steps to the middle note, and then three half steps to the third note, and that makes it a major chord. If we want a minor chord, we see that now the middle note is lower, and now we know that this is a minor chord rather than a major chord. We can read off those frequencies, and then we check those frequencies to see where they are on the piano. We can see, oh, this is the A note, this is the C note, and this is the E note. Therefore, this is a minor chord. And so in this way, you can recognize musical chords. You can listen to a single musical instrument playing a chord, and you can determine whether those notes are, whether those tones form a major chord or a minor chord. So that's really the purpose of this thing that I've called the discrete cosine transform. There's one more step here. And that one more step is that until now, I've assumed that everything is cosines. But if everything is in sine waves, then we get something different. Remember that it doesn't sound any different. The cosine and the sine sound exactly the same to a human listener. So if I take the sine at 440 hertz and the sine at 520 hertz and the sine at 660 hertz and add them together, it will sound exactly the same. Right? That sounds exactly like the minor chord that you heard before. Right? But if we try to do the analysis using cosines, we won't be able to hear it. I mean, the computer won't be able to tell the difference. Look, the computer says here's the blue dots here show the analysis of the cosine chord. The red dots show the analysis of the sine chord. Let me block out the cosine part so that you can see what the sine looks like. Let's get rid of the legend because it's no longer accurate. So if I just show the sine waves, right? The 440 is gone completely. The 520 is there still, but at a much lower amplitude. The 660 is there too, still also, but also at a much lower amplitude. So when I try to do just the sine waves, when the note is created using sine waves, but I analyze it using cosines, I get very bad analysis. It's very hard for me to tell from these red dots that this is a minor chord, right? These red dots make it look like there's only one note there instead of three notes. If I take the cosines, right? If I take the cosine minor chord, then it works out just fine. I've got three clear notes. But if I take the sine wave minor chord, it looks like only one note. And that's a problem because remember, the only difference between the cosine and the sine is their phase. Let me plot these. Let me create a much bigger plot here. And let me plot three subplots. So I'll give it a title saying that this is the minor chord created using cosines. And then let me do exactly the same thing. Let me set layout equals tight here. Let me do exactly the same thing for subfix 1, but using this minor chord created using sines. And then this will all be subfigs 2. All right, let's create all of those. So we see that the minor chord created using cosines and the minor chord created using sines, they even look the same. they sound the same, and they even look the same, just shifted over, right? This downward pulse is then turned upward instead. So the whole thing is just shifted by maybe a little bit. This upward pulse here is downward instead here, right? They look exactly the same, and yet in the frequency analysis, it didn't work. And that's a big problem, right? Because it means that if you just change the timing of your chord a little bit, the discrete cosine transform fails completely, right? And the problem is that in order to detect a sine wave, you need to multiply by a sine wave. We need the W matrix to contain sine waves rather than cosines. If we multiply that W matrix times a cosine matrix, then it won't work. But if we multiply it times a sine chord, then it will work. So now we have this W matrix using sine waves, and now it's working just fine for the major chord that sines. This major chord created using sine waves is being detected just fine by the W matrix created using sine waves, but not by the W matrix using cosines, right? And so somehow we need to include both the cosine and the sine both together in the W matrix in order to be able to analyze the difference between the major chord and the minor chord. Right? So if W is made of cosines, then it can analyze a minor chord made of cosines. If W is made of sines, then it can analyze a minor chord made in terms of sines. We need to somehow include both. We can't just add them together because then we have something that's neither a cosine nor a sine. And so instead, we use this trick called complex numbers. Complex numbers means we create an imaginary signal, right? We have the real signal, cosine of 2 pi kn over capital N, and we'll create an imaginary signal, j times the sine of 2 pi kn over capital N, where j is the square root of minus 1. This is an imaginary number. This number doesn't exist in the real world, but we can make it exist on the computer. On the computer, we simply say, let j equal the square root of minus 1, and then create a W matrix where I have cosine of 2 pi times kn over capital N minus j times the sine of 2 pi kn over capital N, right? This will give us a W matrix on the computer that's half real. This part could exist in the real world. And it's half imaginary. This part couldn't exist in the real world. But no problem. If we multiply, if we take the dot product of x with one of the rows of W, it will equal capital N over 2 if the input has a cosine at that frequency. It will equal j times capital N over 2 if the input has a sine at that frequency. We don't really care whether it's a cosine or a sine, and so we can get back, is there a tone at that frequency or not, by taking the square of the real part plus the square of the imaginary part and taking the square root, which is done using the NumPy absolute value function. So we'll create j is equal to, let me actually make this NumPy square root of minus 1. We'll just take the j number. You can also write it as j is 0 plus 1j or even just 1j. And then W, this W matrix, we have to specify that it's type complex so that the computer knows we're going to have imaginary numbers there. All right. And that type complex will be the cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. Now we can take that W matrix and we can multiply that W matrix times the cosine minor chord. We can multiply it times the sine minor chord, and in either case, we'll get accurate analysis. So invalid np dot square root of minus 1. This is how you write the imaginary number j. Oh, it says that it's not understanding that. So let me write it as 0 plus 1j, just to make it clear that I want an imaginary number. So here we've found the three tones in the cosine minor chord. Here we found the three cosine sines in the sine minor chord. It worked just fine for either the cosine or the sine. Let me try also with the major chord. And Here we have the cosines of the major chord are being detected just fine, and the sines of the minor chord are being detected just fine. And we see that by using complex numbers, by using this trick, basically, where we use complex numbers to represent both the cosine phase and the sine phase in the same entry, in this matrix entry WKN, we do that by having its half real valued and half imaginary valued. And then we take the absolute value here, and that absolute value takes the square root of the imaginary part squared plus the real part squared. And it shows us that, yes, indeed, we do have in both of these a tone at 440, and another tone at 520, and another tone at 660. This is, by the way, what we've done so far now is exactly what's done by the, wow, I'm having trouble centering it. Here we go. It's exactly what's done by the function numpy.fft.fft. Let me look that up. Numpy FFT FFT. FFT computes, it stands for fast Fourier transform. What we've done here is the Fourier transform, and FFT computes the fast Fourier transform. It takes an input signal A, which is just, in our case, that's X, that's the chord, the major chord or the minor chord, and it just takes the Fourier transform of that and returns the Fourier transform. So the output will be a complex NumPy array, which will give you the frequencies. And we can plug it in directly in place of W times X. We can plug in np.fft.fft of the sine minor chord and the sine major chord, and we get exactly the same values that we got before. Right, 400 samples long, so 400 over 2 is 200 samples, and we see that we have a pure tone at 440 hertz, another at 520 hertz, and another at 660 hertz. And so in this way, the purpose of the Fourier transform is to analyze chords. Right? You play a chord on your piano and you want to know what pure tones were in that chord. Well, you can just take numpy FFT FFT, and that will tell you what pure tones were part of the chord that you just played. All right, that's all for the lecture. Let's look at the homework. The homework this week, I think, has 3 different functions in it. Oh, no, it actually has just, yeah, it has 3 different functions. We're going to take a DFT matrix, capital W, which is size n. So it will just be an n by n array, which is cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. And then we'll generate a 1/2 second major chord. So 1/2 second means the number of samples should be 1/2 of fs at frequency little f. And that will give us the major chord, which is the bass note, the root tone, and a major third, 4 semitones up, and a major fifth, which is 7 semitones up. And then we'll do spectral analysis. We'll find the 3 loudest frequencies in X. All right, so first let's work on that major chord. If we run it as is, we discover that we don't have any code written yet. So let me open the homework and start working on that. First, let's start working on the major chord. We don't want the runtime error. Instead, we want to create the note 1 is just the cosine of 2 times pi times the base frequency f divided by fs, and the number of samples that we want. N is going to be fs over 2. We want that to be fs over 2 samples. So 2 times pi times little f times little n over fs. That's note 1. Then for note 2, we need to go up 4 half steps. And so let me create this g, which is 2 raised to the 1/12th power. And then note 2 is a cosine at 2 times pi times g raised to the 4th power times f times little n over fs. And then note 3, the major fifth, That's cosine of 2 times pi times g to the 7th power times f times n over fs. And then what I want to return is the sum of those three notes. All right. So I've created, um, if this is an A major chord, then here's the A note, and here's the C sharp note. It's up 4 half steps from the bass tone. And here's the E note. It's up 7 half steps from the bass tone. Let's try that again. We want to create the major chord at a bass frequency of 256, which is closer to middle C, and then we want to display the resulting note. So um, there's our half second of a C major chord. Let's make it an A major chord. Here's a half second of an A major chord. And we can make it a C major chord up 1 half step from the bass or up one octave. There's a C major chord, and we can go back to the original C major chord. All right, now we've got our C major chord, and now from our C major chord, let's do a Fourier transform. Let's create the W matrix, which is cosine 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. Um, the DFT matrix tells us that we should do that, so if I run that, I should get failure. Oh, here's the tone that has 3 full cycles. Here's where it should fail because it doesn't. I haven't written the code yet. So let's write that code. DFT matrix. It should not raise a runtime error. Instead, I want to create a matrix W, which is maybe zeros of a size of n by n, but the key thing is it has to be complex. And was that a string or was that a tag? Let me see. Let's go back here to where we created a W matrix. D type equals complex, and that should be a string. So D type equals complex. And now let's say that, well, 1J, so this should be for K in the range up to capital N, or N in the range up to capital N. We want W of K comma N to be the cosine of 2 times pi times K times little n over capital N minus 1j times the sine. And then we just return capital W. So we're just creating that matrix. It's the cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. Let's see if that gives us the analysis we wanted. Scrolling down to the homework. Here we go. We want to um, load the DFT matrix, capital W. We want to calculate the fast Fourier transform, and we want to calculate the W matrix times X, and we want to plot both of those, and we should see exactly the same plot. Here's the Fourier transform of that 3-cycle cosine, and notice it has energy here at 3 cycles and over here at 30 minus 3. And here's the Fourier transform again. So the top one is computed using np.fft.fft. The bottom one is computed by taking the matrix multiplication of W times X. All right, now we know how to do the Fourier transform. Now let's use it. Now we want to take the spectral analysis of an 8,000 sample, of an input signal at a sampling rate of 8,000. Looks like this box didn't get filled in, but let's go and test the code first. So we want to find the 3 loudest frequencies. So we want to perform Fourier transform first. Let's set n is equal to the length of x. And let's then create a W matrix. W is equal to DFT matrix with a size of W. size of n, sorry. And then let's find the absolute value of the matrix multiplication of W times the input signal X, and that'll give us our Fourier transform. And now we want the three loudest frequencies, but we only want the three loudest frequencies up to n over 2. So we'll use the argmax function. K1 is equal to NP argmax of um, capital X is the absolute value of the matrix multiply of W times X, and we want the argmax of capital X up to capital N over 2. We don't want to go to the aliased parts, we just want the second aliased parts. And then let's set X of K1 equal to 0 because we don't want that frequency anymore. And then let's find K2 is the new argmax. And then let's set X of K2 equal to 0. And then let's find K3, the third largest node. All right, those are our three frequencies. Now we need to convert them into three frequencies F. So let's do K sorted is equal to sorted of K1, K2, and K3 because we want to sort them in ascending order, so F1, F2, F3, and then we want to multiply them times Fs over capital N. So we want to divide those by capital N. Let's make this an array so that we can do some operation. We want to multiply times Fs and divide by capital N. There we go. So we've sorted K1, K2, and K3, turned it into a NumPy array, and then multiplied it by the sampling frequency and divided by the number of samples. I think that's what we want to return. So we have three frequencies, the three peak frequencies of the chord, and we want to return those frequencies in hertz. Let's go and see if that gives us reasonable values. Here we have F1, F2, and F3. We have X is equal to let me take the major chord actually. Let's just take the major chord and let's find out what its three major frequencies. Okay, it hung up somehow. W is equal to DFT matrix N, X is equal to, oh, because I created a very, very large W matrix, didn't I? Maybe I don't want to do it that way. Maybe I should use the FFT. Let me go back here and use the FFT instead. Instead of creating a whole W matrix, I'll use the FFT because that will be faster. And what else do I want? F sorted is a NumPy array. I'm supposed to return this as a tuple though, so let me turn that NumPy array into a tuple. F1, F2, and F3. Actually, let me just return it as let me return them value by value. F sorted 0, F sorted 1, and F sorted 2 just to get all three of them to come back. So I'll save that. Let me go over here and see it still hasn't calculated, so let me stop that and let me try running it again and see if it works now. The three frequencies are 440, 555, and 660. Right, that's the difference between using np.fft.fft and w times x. The difference is that the FFT is much, much faster. Let's try running the grading code and see if it works. Ran 6 tests in 0.024 seconds and it worked 100%. All right, so let's go ahead and check it into GitHub. All right, we'll check in homework 7. The diff is too large to be displayed, but we can push it to origin. All right, now that it's been pushed, let's go to my GitHub. This is my student account and see if it's loaded. Here's the student account. Let's go to Intro Speech Understanding, Lecture 7, Homework 7.py, and we have the major chord, the DFT matrix, and the spectral analysis is all there. So we can copy this and then go to the course web page, the Canvas page. And on the Canvas page under Homework 7, we have, please enter here the URL of your copy of Homework 7.py. So go ahead and complete Homework 7 and submit it there, and I'll grade those as soon as they're submitted by next week if you have them submitted by then. Thank you. Let me now stop recording and then we'll take attendance.